Turn on your faucet and take a refreshing sip of water. Approximately 780 million people around the world don't have access to such a luxury. According to the World Health Organization, 3.575 million people die each year from water-related illnesses. Water can get so bad in certain areas that people will quite literally be bathing in and drinking water that is contaminated with their excretions, both urinary and fecal. My project deals with the global nitrogen water pollution problem, which is a threat to public health and the environment. Nitrogen pollution can be caused by sewage treatment effluents and surface runoff from fertilizer application. Locally, pollution can be caused by contamination from the excretions of marine organisms and humans. To remove nitrogen from water, industry traditionally uses an expensive, energy-intensive, and multi-step nitrification-denitrification process where ammonium is converted into nitrites, nitrates, and then nitrogen gas. Now, as you can probably imagine, this sort of expensive process isn't available to developing nations that need it the most. So this study's objective is to address ammonium pollution by harnessing cellulose sulfate from jute for ammonium recovery. Ammonium can be recovered from the very beginning, minimizing the multiple steps normally needed for remediation of nitrogen from water, and thereby reducing the costs associated with the nitrification-denitrification process. Modified cellulose biomasses have become popular for water treatment due to their accessibility, high efficiency, cost effectiveness, biodegradability, non-toxicity, and easy handling. In past research, celluloses containing sulfonic acid groups have been used to capture charged water contaminants such as heavy metals. Underutilized cellulose biomasses for water treatment upcycles biomaterials with negative value and turns them into materials that have positive value to improve both health and the environment. To go about addressing the objectives, I synthesized 3 separate cellulose sulfate materials based on 2 reactions that were run in parallel to each other. Now, before conducting these reactions, a pretreatment protocol was necessary, where raw jute was bleached in a solution of acetic acid, sodium acetate, and sodium chloride, and this was done 2 times to remove lignin and hemicellulose. Following the bleaching process, there was a mechanical grinding process which essentially broke the raw jute into very small, fine pieces so that the sulfonation reactions could be more efficient. Following the pretreatment process, the sulfonation reactions were attempted. Basically, 2 parallel reactions were run. One reaction was run to synthesize nanocrystals, and the other was run to synthesize microfibers. The nanocrystal reaction involves suspending 10 grams of jute, which was bleached and mechanically ground, into 200 milliliters of dimethyl formamide, which is an organic solvent. Following this, 4 milliliters of chlorosulfuric acid was added, and the reaction was allowed to run for 5 hours. In parallel to this reaction, the microfiber reaction was run, where 10 grams of jute was suspended in 200 milliliters of the same organic solvent, and 2 milliliters of chlorosulfuric was added and allowed to run for 12 hours. Following the microfiber synthesis, a portion of the product from the microfiber reaction was homogenized at 500 bars 2 times to yield nanofibers. Once the materials were characterized, a concentration study was attempted on all 3 of the materials. Essentially, what the study involved is the addition of ammonium in a 1-to-1 ratio to each respective CS material. Following a 1-hour period, the supernatant was extracted, Nessler's reagent was added in order to visualize ammonium within the supernatant, UV visible spectrophotometry was attempted in order to calculate the concentration of ammonium in the supernatant compared to the concentration that you started with initially. And using that difference, we could tell how efficacious each material was in removing ammonium from solution. Practical applications were explored, the first of which is the sustainable fertilizer study. Now, essentially in this study, I sought to answer the question of whether my materials, once they recover ammonium from water, could be applied as sustainable fertilizers for plant growth. To go about this, I had an experimental setup that involved 4 conditions. The first of which was a starter fertilizer, which was commercially available. The second of which was microfibers that were ammonium loaded. The third of which was nanofibers, which were ammonium loaded. And finally, a control with no fertilizer. Now, the reason why nanocrystals were not used was because the reaction had low yield because of such high acid that it was very difficult to get enough of the product in order to test it. The second main practical application that was explored is the column filtration study. This involved adding a small amount of CS material to a column filter, which uses gravity in order to filter 200 milliliters of a certain concentration of ammonium wastewater. And the flux of the column was calculated, and additionally the removal efficiency of the material was also calculated. So now on to the results and discussion. Zeta potential confirms that nanocrystals have the most negative surface charge, followed by nanofibers, then microfibers. The pH value has no significant effect on zeta potential, which confirms the cellulose sulfate charge hypothesis that I had previously mentioned based on the industrial resin data. Now, the reason why this is very important is because when considering the issue of ammonium pollution, as I had previously mentioned, it can be due to things like animal and human excretion, which when you urinate, that solution that is the product of the urination is filled with protons, and therefore the acidity of it is altered. So you need materials that can remain efficacious through varying acidity levels, and this material offers that benefit. Fourier transformed infrared spectroscopy, or FTIR, of nanocrystals, nanofibers, and microfibers all show OH stretching at 3,342, CH2 stretching at 2,901, and S double bond O stretching at 1,219. Now, essentially, what the OH stretching and CH2 stretching confirm is that all materials have a cellulose backbone. What the S double bond O stretching would seem to confirm is that sulfonation was successful for all three materials. Scanning electron microscopy images confirm that nanocrystals and nanofibers exist in nanoscale and that the microfibers are partially defibrillated and have a larger bulk morphology. Energy dispersive spectroscopy, or EDS, confirms the presence of elemental sulfur in each of the three materials, which combined with the FTIR data would seem to strongly indicate that sulfonation was successful for all three materials. Contact angle is a technique that looks at hydrophobicity and hydrophilicity by adding a water droplet onto a dried membrane of a given material. So this reveals that nanocrystals have an average contact angle of 60.05 degrees, followed by nanofibers, which have an average contact angle of 41.05 degrees, and microfibers, which have an average contact angle of 21.90 degrees. The smaller average contact angle in microfibers is due to a more porous surface compared to nanofibers and nanocrystals, where that water droplet can flow through more efficiently. And so in the nanofibers and the nanocrystals, you see less of that sort of open space where the water can flow through. The concentration study indicates that ammonium removal increases with increasing equilibrium ammonium concentration, with the maximum absorption capacity from the Langmuir isotherm achieving 88.22 milligrams per gram for nanocrystals, 68.71 milligrams per gram for nanofibers, and 5.97 milligrams per gram for microfibers. By comparing the maximum absorption capacities of my materials to materials that are listed in literature, it can be noted that my materials are all competitive with materials that exist in the literature, with the nanofibers and nanocrystals being particularly competitive. But even with the nanofibers, which technically is the reaction that involves the less application of acid and no energy cost because of homogenization, still being competitive with things like slag. In the fertilizer study, it can be noted that the ammonium-loaded microfibers and nanofibers promoted more plant growth throughout the 5-day period than the control with no fertilizer, suggesting that my materials can serve as successful, sustainable fertilizers. Overall, the ammonium-loaded microfibers promoted more plant growth than the ammonium-loaded nanofibers, possibly due to the superior hydrophilicity of the microfibers as determined by contact angle. Again, because of those larger pores, which when you water the plants, the water will sort of release more nitrogen, allow for more potential plant growth. Plant growth from the commercial fertilizer leveled off in the last 2 days, while the ammonium-loaded microfibers and nanofibers continued promoting growth, suggesting something interesting, that maybe this commercial fertilizer has a built-in slow release mechanism that allows it to steadily release over the last 2-day period, whereas potential further direction of study for my materials would be how to sort of incorporate that process of slow release, just as is seen in the commercial fertilizer. Column filtration is a practical method of implementing my adsorbents, and what I found was that using 0.38 grams of microfibers in 200 milliliters of simulated wastewater, there was an 88% reduction of ammonium in the effluent, and the calculated flux of the column was 3 milliliters per minute. The main conclusions of this study are that cellulose sulfate nanocrystals, nanofibers, and microfibers are effective materials for ammonium removal, that ammonium-loaded cellulose sulfate materials can be used as sustainable, safe, non-toxic, and biodegradable fertilizers, and that cellulose sulfate materials are resistant to changes in wastewater pH, which makes them effective, inexpensive, and practical for ammonium removal. Additionally, it's important to note that cellulose sulfate microfibers can be implemented practically through column filtration, and potentially nanofibers also if you were to implement something like a fluidized bed. Down the road, this technology may be applied to mitigate global health threats, improve agriculture through sustainable fertilizer application, scale fish farming operations for healthy food production, and mitigate harmful algal blooms all across the world. With that, I thank you for listening to my presentation and wish you a nice day.